Well, hi everybody, I'm Paul Gross. Thanks for joining me. Glad you could be with me for my climate change webcast. This is a live broadcast, no scripts, no teleprompter, and no politics. We're just going to be talking about science here. And before we get started, a couple of very quick orders of business. First of all, I want to remind you that I'm going to be using the terms climate change and global warming interchangeably. There is no political implications. Don't read anything into that. It's just I use the terms interchangeably. And also, I want to repeat my promise. Some of you have heard this before. I want to repeat my promise that I will only bring you science directly from the science community. I will never, ever share with you any information that comes from advocacy groups. I am not accepting any information from those groups. I will not share any of that with you. Everything that I've shown you on Local 4 and here on clickondetroit.com has all been straight science, straight from the scientific community. So all right, let's get started here. We're going to start with the science itself, and then we're going to get into the indicators of climate change, some of the impacts of the change, get into some of the local impacts we're feeling right here, and talk a little bit more about the future. We're going to start by talking about the greenhouse effect. And the greenhouse effect has taken a real negative connotation over many years because of the greenhouse gases in the atmosphere that people talk about with a negative connotation. But there are really only three things that really dictate a planet's temperature: how close it is to its sun, or in our case, the sun, or its star. You have the surface color, the albedo of the planet, in other words, the color of the planet, and then you have the composition of its atmosphere. Now, we have not changed our distance from the sun, and our surface color hasn't changed either. So the only thing we're going to talk about today really are these gases. And here's how the greenhouse effect works, real briefly. A certain amount of energy comes to Earth from the sun. Some of that escapes back into space, and some of it is kind of held in by certain gases here in the atmosphere. Now, we need this greenhouse effect. Without these greenhouse gases in the atmosphere, instead of the temperature that our planet has now, we would have a temperature of 0 without those greenhouse gases. So we actually need this greenhouse effect. So let's talk about those gases themselves. Now, 99% of our atmosphere is nitrogen and oxygen. There are four main gases that we call greenhouse gases that kind of trap heat: water vapor, carbon dioxide, methane, and nitrous oxide. Those are all kind of grouped together in that 1%. But even though it's a small percentage, it's very, very important, as you will see. Now, some people like to try and tell you this whole science of global warming is something recent. No. This goes way back into the 1800s. Back in 1863, John Tyndall actually predicted that doubling carbon dioxide in the atmosphere would warm the Earth's surface. And then in 1895, Svante Arrhenius, he actually went further and got more specific, and he actually predicted that the Arctic would warm by 15 degrees if we increase carbon dioxide in the atmosphere by 2 to 3 times. And actually, his prediction that the higher latitudes, in other words, the poles, would be most dramatically impacted, actually, that is coming true. We're seeing some of the greatest temperature anomalies at the poles right now from the warming. So this science goes way back into the 1800s. Now, a lot of people also like to talk about the fact that we've had cycles throughout the Earth's millions and billions of years. We've had cycles. Yes, we have had cycles. Temperatures have gone up. Temperatures have gone down. But the important thing you need to remember, all of those previous cycles, if you will, were caused by astronomical things. Things like the Earth's orbit around the sun, little changes there, changes in our tilt, changes in the rotation. The Earth sometimes, it kind of wobbles a little bit. We call that the precession of our axis. So all of those previous warmings were caused by astronomical changes. That's been determined. Our current warming, none of this has happened. None of this has changed to cause the current warming. We'll get more into some of the hows and the whys. But first, a lot of people ask me, how do we know what the Earth's temperature was and what our atmosphere was made up of over so many hundreds of thousands of years? Well, believe it or not, we actually do know, and it's hard and fast data. It's not speculation. Things like ice cores in the poles, where you have these enormous miles of thick ice over the hundreds of thousands and millions of years, that ice traps bubbles of air. Scientists drill ice cores, extract the air from those bubbles, and they actually know the composition of our planet's atmosphere going back, in some cases, 2 million years. So we have other things. We have, like, for example, sediment cores they drill at the bottom of the ocean. We have tree rings, more recent, detailed data. Same thing with corals. So we have a lot of data that gives us relative measures of temperature over a long period of time. All right, let's show you some of the actual data. This is carbon dioxide in the atmosphere going back 800,000 years. So this is 800,000 years ago right here, all the way to the present. And if you look, we have had oscillations of carbon dioxide. Every time the Earth warms, it releases more carbon dioxide in the atmosphere, and we see a spike. And so there's lots of ups and downs here. Yes, we've had oscillations of carbon dioxide, but notice that those oscillations, those peaks of CO2, carbon dioxide in the past, they were all between 250 and 300 parts per million. Look at what's happening now since the beginning of the industrial age. We have gone basically exponential, straight up. We're at 400 parts per million, and it has not been anywhere close to that over the past 800,000 years, and there are new studies out that say that we have not been close to that number in 2 million years. This by itself is an extraordinary piece of data that shows you that humans, it's hard for people to actually comprehend this, but we humans have actually changed the composition of our planet's atmosphere. And I'm going to say that one more time because it's stunning. We have changed the composition of our planet's atmosphere. All right, let's get into something that other people like to talk about, and that is solar activity. A lot of people like to try and blame some of this stuff on solar activity. This red line here, this is temperature relative to average. In other words, above or below average for any particular year from the mid-1800s to the present. The blue line here is carbon dioxide, and you can see how these two lines kind of match up a little bit in terms of the trends. But this line here is sunspot number, in other words, solar activity. And you'll notice, you see this very sharp warming right here in the red curve here, matching up with the carbon dioxide. But notice, there is no correlation with sunspot activity. So we can kind of rule out changes on the sun in terms of a cause of this particular current warming that we're undergoing right now. All right, I actually showed you this in the last couple of climate change webcasts, and it's worth showing you again because I consider this probably the most important slide in this entire presentation. I call this the smoking gun slide, and the reason is, everybody asks, but how do we know it's the human activity that's causing the warming? Well, the kind of orangey line here, kind of that orange line here, those are actual temperature observations, global temperatures from 1890 to the present. Now, the green line here, those are climate models predicting what all of these temperatures would have been when you put in the old data, what the climate models would have predicted, and these models include everything. Natural forcings on the climate, things like volcanoes and things like that, and also the increase in greenhouse gases from human activity. This blue line here, those are those same climate models with one change. The scientists took out the human increase in the greenhouse gases. In other words, the scientists took out the human activity but left in all of the other natural forcings on our planet's climate. Notice that this green line matches up real nicely here, especially in the past 50 years, but matches up real nicely in terms of the climate models showing the warming that has already occurred. And yet, if you take out the human activity from the climate models, those models actually suggest that our planet has cooled in the past 60 years or so, 50, 60 years. And we know that that's not the case. So this is something that really shows the human impact, the human footprint on the warming climate. And keep in mind also that the particular type of carbon dioxide in the atmosphere, scientists have typed that. In other words, they have matched that up to the particular type of CO2 that's emitted from industry and things like that. So we actually know that the type of CO2 that's actually increasing in the atmosphere by its nature, by itself, is the result of human activity. All right. As I mentioned, though, there are three main greenhouse gases that are not naturally occurring. Water vapor, of course, is naturally occurring. We have methane, we have carbon dioxide, we already talked about, and we have nitrous oxide. This goes back to the year 1000. So we're going back 1,000 years, all three gases on the same graph, and notice, very, very consistent, very steady, unchanging levels of these gases going all the way till you get to this orange area here, which is the start of the Industrial Revolution. And right after we started industrializing as a society, all three of these gases started increasing very, very rapidly. So it's not just one gas that we're cherry picking. The three main greenhouse gases that we're talking about here, carbon dioxide, methane, and nitrous oxide, all of them started increasing in our atmosphere with the start of the Industrial Revolution. So again, it's not an exaggeration to say that we have actually changed our planet's atmosphere. We have actually done that. All right. If you're wondering, by the way, what's the percentage? Well, carbon dioxide is about 82% of it. 10% is methane, 5% nitrous oxide, and by the way, 3% is fluorinated gas. But what's more interesting, actually, is where is all that coming from? Well, 31% of those greenhouse gases are coming from electricity production, 27% is coming from transportation, and then you see the number starting to drop. Industry is about 21%, commercial, residential impacts are about 12%, and about 9% comes from agriculture, from farming. So as you can see, well over half of these increases in greenhouse gases are coming from transportation and electricity generation. So that's kind of where those gases are coming from. I thought that you'd find that kind of interesting. One last thing in this section, and that is the scientific consensus. Now, probably one of the greatest comments I get from people is that nothing is settled and that this is just something that is just in great disagreement among the science community. That is an actual false statement. A study was done. They surveyed actively publishing climate scientists. 97% of them agree with human activity being the proximate cause for the warming of the climate. But some people weren't satisfied with that. So another study was done. And what they did this time is they went to the scientific research journals and they actually surveyed the articles, the research articles that were being published in those journals. And the number now, 99.9% of that scientific research in the peer-reviewed scientific journals, those papers agree with a proximate cause of human activity for the current warming. And by the way, I read this paper here, and the words they use to describe the number of papers coming in with an opposing viewpoint, their words are, those papers are, quote unquote, vanishingly small. So we are seeing a large body of evidence from scientists all around the world about all of this data and all of this information that I'm showing you here today. All right, let's get into some indicators, indications of the warming climate. This is kind of a repeat, but in a different format, showing carbon dioxide, which is this yellowish line right here, and global temperatures over the past, going back to 1880, the start of official temperature records. And you can see, again, the great correlation, carbon dioxide increasing, temperatures kind of increasing right along with it. And as I showed you before, our carbon dioxide levels are at the highest that they've been in 2 million years now, 2 million years. Another indicator, the 10 hottest years that our planet has had have all come since 1998. And I'm going to show you more in detail in a minute, but look at last year, 2015. Look at how much. If you compare that to the other 9 warmest years that our planet's had, look at how much 2015 is above all of those other years. And by the way, last year was the 39th consecutive year that the planet has had an above average temperature. And in case you're wondering, when's the last time that our planet has had a record cold year? Think about it. What do you think? The last time our planet has had a record cold year is over 100 years ago. Over 100 years ago. I'll let you just think about that. All right. Let's talk about, again, this is one reason I like to use the term global warming sometimes instead of climate change, because it's a global warming. It's not just the temperature in Sterling Heights or in Michigan or in North America. It's the entire planet. So let's look at last year for the entire planet. And if you look at this, the reds and pinks are above average temperatures. And in fact, the red here, anything where you see this dark red, those are record hottest temperature for the year ever for that area. And there's one notable cool spot off of Greenland. We think that could be cooler waters from the melting ice pack, that melting snowpack on Greenland, which could impact a very important circulation pattern here in the Atlantic called the AMOC. So we're going to be keeping an eye on that because those ocean circulation patterns have a tremendous impact. But look at, basically the whole world was above average for temperatures for 2015. But a lot of people like to say, yeah, well, Mr. Wise Guy, that was all because of El Nino. We all know about El Nino. Well, you know what? Scientists have already done that research. And it would have been one of the warmest years on record even without El Nino. And let me show you something. This is one of my next most favorite slides in this entire presentation. Each bar here is an average temperature for the planet relative to normal. So 0 is kind of the average line, so below average or above average for the planet. This starts in 1950 and goes to the present. What I want you to notice, some of the bars are colored orange, some of them are colored blue. The orange bars are El Nino years. The blue bars are La Nina years. Now, El Nino is an eastward shift of those warmest ocean waters in the Pacific, and a La Nina is when those ocean waters, those warm waters, shift westward. Has a tremendous impact on the jet stream and other things. Now, El Nino years are generally warm years for the planet. La Nina years are cool years for the planet. Look at what's happening. I want you to focus on the blue bars. Look at what's happening. These blue bars, which back in the 1950s were cooler than average years for the planet, even the cooler La Nina years are getting warmer. And now, a La Nina year is actually warmer than what an El Nino year was back, in the 1950s. So we have these El Ninos and La Ninas, and yes, they have an impact on global temperature, but the warming of the overall large-scale climate is actually impacting the years that our planet is having, even when we have those El Ninos and those La Ninas. So very, very important, and we're watching to see if the frequency and the intensity of these events, these El Ninos and La Ninas, is being impacted by the warming of the climate. All right. Some people like to say, well, you're just cherry picking temperature data from one research institution. You're fitting the one that you like the best into all your stuff. Well, no, let me show you this. There are actually 4 different lines here on this graph here. Okay? These are 4 different international climate research centers, their computations of world temperatures from 1880 to 2014. Okay? You have NASA, you have NOAA, you have the British Meteorological Office, and you have the Japanese Meteorological Agency. 4 independent research institutions. And notice how very aligned and close all 4 of these lines are. 4 different major international research centers basically coming up with the same exact computation from all the data available of the globe's temperatures since 1880. So there is great agreement on what has already happened among these 4 major research institutions. And here's something that's going to actually surprise you. This is a new slide this year. All this warming we're talking about, guess what? 93% of all of this excess heat that's coming into our planet and staying here, 93% of it is going into the oceans. Only 7% of the excess heat is staying here on the land, the air, or in the ice. So that's a real important thing to think about. Let's say, remember, our planet is like it's 3/4 ocean water. Let's say our planet was only half ocean and half land. We would be much, much warmer over the land where we live because there'd be much less water to take in that excess energy, that excess heat. So we're seeing 93% of this warming right now going right into the oceans. And yes, the oceans are heating up. What you're looking at here is the change in ocean sea surface temperature since 1901. Okay, so we're going back for over 100 years now. And again, look at, why I call it global warming. Basically, the entire world's oceans are much warmer than average over the past 100 years. That warming has progressed, and especially over the past 50 to 60 years. And there's that little cool spot off of Greenland. Again, we're watching that very, very carefully because that could impact the Gulf Stream and have significant implications on places like Western Europe. They are watching that very, very closely. All right, so what is this warming doing to the oceans in terms of what it means for you? Well, guess what? Sea level is rising. And it's not just because we're seeing melting of the ice packs on Greenland and in Antarctica. What most people don't understand is that water is a very interesting substance. When you warm up water, the water expands. It's called thermal expansion. So this is sea level from 1880 to the present, and you can see a very steady rise in sea level. But again, some of that is happening just because the ocean temperature is increasing. Yes, the warming of the waters by itself is increasing sea level, and then that's being added onto by the melting of some of our polar ice packs. All right, some people are wondering, well, historically, how is this sea level rise playing out? Well, we're going back 2,000 years for you here, 2,000 years, starting with the 1st century all the way to the present. So this is above or below average sea level. Okay, for each century. So that takes away like year to year weird things that might happen. So this is for an entire century. Okay, and if you look, there are little ups and downs. But look what happened in the 20th century. Look at the sea level rise. You go back 2,000 years, you cannot find another year, or I should say another century, in which you're seeing this level of sea level increase. So yes, we are seeing the highest sea levels over the past 2,000 years in terms of the rate of increase, and right now it is not showing any signs of stopping. All right, this is interesting. This is polar ice. This is North Pole ice, okay? And just take a look at this animation. You're actually seeing this year by year. Look at how you can just see before your eyes the ice pack is shrinking. Look at that. The ice pack is shrinking, and not only is it shrinking, but in areas where they're still seeing some ice here, the ice has thinned. And that thin ice is really important as well, because that melts very quickly once you get into spring and summer. That thin ice melts quicker. And then once you get rid of the ice in the summer, a lot of it at least, you have the sun now hitting water instead of ice. Now that ice is white and that reflects the sun's radiation. But when you have ocean water instead of ice, that darker color of the water, that absorbs more of that solar radiation, and that heats up this polar water here, and then that helps to slow the increase of ice as you get into the cold season. So we are seeing a very definitive decrease in our polar ice there at the North Pole. All right, what about the Great Lakes? We'll just kind of get a little closer to home here. We are seeing a very steady decrease in Great Lakes ice cover since 1973. Now notice, yes, there are big ups and downs. We had some brutally cold winters in the mid-70s, so yeah, that ice was way above average. 2 and 3 winters ago, we had those 2 really rough winters, and yeah, so that ice was up. The Great Lakes ice was up in those 2 winters too. But if you look at the whole period from 1973 to the present, Great Lakes ice is decreasing. You know what that means for you? More lake effect snow. So keep in mind that even with a warmer climate, you can get more snow, and we'll talk more about snow in just a little bit. All right, what about the glaciers? You're looking at 2 pictures of Muir Glacier in Alaska, taken in 1941 and 2004, taken from the exact same spot. All right, take a look at that. I'm going to step out of the way so you can take a look at that. There's a huge ice sheet right here back in 1941. And here, look, you have a lake here. In 2004, you have a lake here. The glacier has retreated by 7 miles in that period, and the thickness of that glacier has decreased by 1/2 mile. So these are the types of things, these are the types of indicators that we're seeing, things that we're seeing that are resulting from the warming. All right, see this the way it is right now? If you had an equal number of record warm and record cold, you'd have that kind of that even distribution, an equal size for the blue and the red. But look what's been happening, okay? We're looking at the ratio of record warmth versus record cold. And look what has happened. Again, this green line here, if you can see it there, this green line right here, that would be kind of a normal, equal distribution of warm and cold. But look what has happened. Everything has shifted to the right here. Look at the size of this red area here. Many, many, many more record warm readings that we're seeing versus, look at the blue here. That's record cold. So we are seeing a very decided shift with an increase in record heat versus record cold, and I'm going to break that down on a local level for you in just a few moments. Just for something out west, if you have friends or family out west, with what's happening, we're seeing a very decided increase in wildfires out west. You've seen it on the news. You know what I'm talking about. This goes from 1970 to the present. Look at the very enormous rate of increase in those western wildfires. So it's not just in one place or another. The whole world, various regions are seeing changes, indications from the warming of the climate. All right, so let's talk about some of the impacts, the actual impacts. Interested in extreme weather? Sure you are. You want to know, like remember that flood we had in August in 2014, stuff like that? Heavy downpours are increasing across the entire country. The greatest increase is here in the northeastern quarter of the country. New England, it's a 71% increase. Here in the Great Lakes and the Midwest, a 37% increase. So we're seeing, Chuck Gadiger likes to call it extreme extremes. We're seeing more of the big ticket precipitation events. And to break it down for some of you, some of you just want to see the actual data, not just a map. Here's the data. Days with 2 inches or more of precipitation, you see a very decided increase right here. This is a very noticeable increase from 1950. And yes, there are oscillations. There are years with more and years with less, but you have to look at the overall trend, and the trend is very noticeably upward. All right, what about 3-inch rain events? Even more extreme. Well, these are days with 3 inches or more of rain, and again, you see there's still an increase occurring with those extreme precipitation events. People ask, why is that happening? You know why? It's a very simple concept. As you warm up the planet, you evaporate more ocean water into the atmosphere. That becomes water vapor that's available for storm systems to tap into. So, if you have more water vapor in the atmosphere and you have a good-sized storm system, there is more water vapor available to turn into precipitation. And we're seeing an increase in these extremes all around the planet. This is just data for the United States. All right, raise your hand right now if you have allergies. All right, how many of you raised your hand? Come on, this is a webcast. All right, if you have allergies, you need to see this. Right now, okay, right now we're talking about grains of pollen from grass production, okay, grass pollen, okay. Right now, you can see the level here, about 7 or 8 here on the graph here, okay. And if you notice, if you go up to 2060, the year 2060, look at the increase in pollen production from grass. Now, if you go up to the year 2085, look at this. We are going to see, as we increase the carbon dioxide in our atmosphere, a much higher production of pollen in the air from our pollinating plants. So if you have allergies, this is something that as we move through this century, it's just going to get worse and worse and worse in terms of the exposure, at least. Now, again, I can't comment on medical breakthroughs that might be able to mitigate the symptoms, but I can certainly tell you that based on what we're seeing with the climate, we're going to see an increase in pollen production as we move through this coming century. All right, let's get into some of the local stuff. You want to talk about our area. I hope you can see this. Let's see, I'm looking at the monitor here. Yeah, I think you'll be able to see this. Okay, there are 3 lines on this graph. This is for Detroit, okay? This white line right here is our average daily temperature for the entire year. Okay, so you got winter, spring, summer, fall, each one coded by color here. And so you can see how the temperature rises as you go through spring into summer, where it peaks and then it drops off in the fall. The yellow line here is if cuts are made in emissions. In other words, we reduce the emissions in the atmosphere, we still notice that line gets higher. So we're still going to see some warming. We're past the point of stopping the warming. All we can do right now is slow down the warming. So if anybody ever tells you we have to stop global warming, that isn't by itself is an extremist view. We cannot stop the warming. Even if we go cold turkey right now and just cut them all, the emissions, we can't stop it right now, but we can slow it down. And if we just leave things unchecked, if we just let the emissions go as we're doing them right now, this orange line right here shows average temperatures each day of the year projected by the climate models. And what's really interesting is in the summer, for a good part of the summer, our average high temperature is above 90. And this is by the year 2100, by the way. So our average temperature in the summer would be above 90, well above 90 for midsummer by the year 2100 if emissions are left totally unchecked. So basically, as a climate scientist once told me, he specializes in regional climate change. He told me once that by the year 2100, he said a southeast Michigan summer is going to feel like a southwest Missouri summer it does today. So that just gives you some indication of possibly where we're heading. All right, so let's talk about, I did my own little research project here. And what I did is basically I counted the numbers of record highs and record lows. And keep in mind for each day, you can have 3 different record warm or record cold. You can have a record high, for example. You can have a record for the warmest low temperature. And you can have a record for the warmest average temperature for the day. And the same thing with cold. So you can have 3 possible warm or cold records on any day. And I counted them all. So we have a climate record here that goes back to the 1870s. If we had no change in our climate, if everything was just kind of steady state, it wouldn't be exactly 1-to-1, but you would have nearly an equal amount of record warmth versus record cold. So I counted in the decade of the 1990s, we had a 3-to-1 ratio of record warmth versus record cold. Now 3-to-1 by itself is really unusual, okay? So that shows an unusual warm forcing on the climate. In the decade of the 2000s, look at that. 3-to-1 was unusual. we jumped up to 6-to-1 as a ratio of record warmth to record cold in the first decade of the 2000s. What about the current decade? Yes, I am still counting. We now have 86 warm records so far through this decade, and we've had 25 cold records. But keep in mind, 22 of those 25 cold records occurred with those two severe winters we had 2 and 3 winters ago. And those were unusually severe winters. So you can see, even with those 2 severe winters, we still have around a 3-to-1 ratio of record warmth versus record cold. So we are seeing an impact here in the form of more record heat. It's documented. I just took this straight from the weather records. I just did the counting myself. What about snow? Everybody likes to talk about snow around here. You either love it or you hate it. Are we seeing an impact? Yeah, we are. Guess what? 6 of Detroit's top 15 all-time snowiest winters have occurred just since the year 2002. That's right. In the past 14 years, we've had 6 of our top 15 all-time snowiest winters. And the reason goes right back to what I told you earlier. With a warmer planet, you evaporate more ocean water in the atmosphere, and that ocean water becomes water vapor in the atmosphere, which the storms can use to create precipitation. Look at this the storm we had this past weekend. You know, that was not a powerful storm that came through the area. It was a very modest storm. It just was a slow-moving storm with a lot of moisture. So you can get a snowier winter even in a warmer climate if the storm track is right. And you combine this with what I told you earlier about the Great Lakes ice is decreasing. That means more lake effect snow. Yeah, we could have potentially in some winters a lot more snow than average just because of the warming climate. I know it sounds counterintuitive, but that's what the facts are. All right, warm summer nights. This is something actually that's kind of interesting because everybody focuses on the high temperature for the day, but our nighttime temperatures are going up too. This goes from 1970 to 2014. This is for Detroit. This is for us. Notice that the nighttime lows are going up as well. Now you're thinking, well, I'm sleeping. Why is that important? Well, I'll tell you why it's important. When you have, say, a heat wave going on, nighttime is the only time that we have to kind of relieve some of the stress on our bodies, especially people that don't have air conditioning, and also plants and animals too. So if you're now increasing the overnight lows, then when you have heat waves, what's happening is you're having less of an opportunity to recover from some of that daily stress, and that long-term added stress is not good. It's detrimental, whether you're a human or a plant or an animal. It's just not good. So we're seeing overnight lows increasing. In fact, in a lot of cases, the overnight lows are going up a little more than the daytime highs, actually. So that's an important component. But what about cold nights? Days with nighttime temperatures below freezing. Well, we're seeing a drop in those. In fact, a rather noticeable drop from around 140 or so down to, let's see, by the current time, it looks like we're about 118 or so. So we are seeing a drop in the number of nights with temperatures that drop below freezing. So some of that's good news, for example. Maybe your heating bills are going to be dropping because you're not going to be quite needing as much heat. But the other thing that's bad is that we need a periodic Arctic blast over the course of a winter because those Arctic blasts kill some of the pests that cause us problems in the summer. So if you have milder winters with fewer freezing nights, you're going to kind of kill off fewer of those pests. So that's another area of research right now are these pests starting to overwinter in greater numbers than they used to because the temperatures are starting to come up. So that's another area of research people are watching. All right, this slide, and I've already answered a bunch of questions that some of you have asked on our Local 4 Facebook page, but this is one that a lot of people are asking, and I put this slide in here just to take care of your questions. People are asking, are we seeing a change in our seasons? Well, this is kind of cool. What we're looking at is the warming from 1970 to 2014 by season here. This is, again, strictly for our state, for Michigan. We're looking at the warming by season. Now, spring, summer, and fall are these 3 lines that are grouped right here. Notice spring, summer, and fall are all warming almost identically. But the one season where, again, this is over the entire period of time, don't just think about 2 winters ago. We're talking about the entire period of time from 1970. Winters are increasing in their temperature relative to the other seasons by a lot more. So we are actually seeing a change in that our winters are starting to get warmer as part of a long-term new average. And so some people are also asking about the starting and the ending of winter and things like that. I haven't done research into that, but like some of you, I've kind of noticed that that it seems like winter is a little later in starting in some years. I mean, we tend to have nicer falls right now, and the cold air doesn't quite come in quite as early, and that's something I'm going to maybe tackle as a future research project, and I'll let you know about that for sure. But yeah, our winters are warming much quicker relative to the other 3 seasons. Okay, we're almost done here. Just three more slides here. Just again to put into a numerical context for you so you can really understand this. Okay, what is our future in terms of 90-degree days in the summer? Right now we average 13 90-degree days. 13. By the year 2060, we will be averaging 37 90-degree days if, again, emissions continue as they are right now. By the year 2100, think about this. We will average 68 90-degree days. So think about that. Right now, we average 13 90-degree days every summer. By the year 2100, that's when our grandkids are going to be living in this stuff, we'll be up to about 68 90-degree days every summer. And so, again, depending on what we do with emissions over the coming decades, we could slow the warming and maybe these numbers go down, hopefully. Or if things are left unchecked, well, maybe this is what's going to verify. We'll have to see. All right. Back to those nights below freezing, again, to put it into specific numbers for you, right now we average 118 days a year with a nighttime temperature below freezing. By the year 2050, that'll drop to 83. By the year 2100, that'll drop to 52, more than half. So again, we're seeing that marked decrease in overnight temperatures in terms of the number of nights below freezing. The actual overnight temperatures are going up, but those numbers of nights with temperatures below freezing are going to be dropping precipitously, again, by more than half just in the next 75 years or so. All right, last slide here. Carbon dioxide, and this is, again, the reason why we say even if we were to go cold turkey right now, we're not going to see an immediate impact. Carbon dioxide remains in the atmosphere for hundreds to thousands of years. So everything that we keep putting into the atmosphere is adding to that change in our planet's atmosphere that I already talked about, and so that kind of stays there for a while. So it's sort of like when you put a pot of cold water on the stove, you turn on the burner, and it takes a while before the water starts boiling. But then keep in mind, when you turn off that burner, it's still hot for a long time before it comes down to room temperature. So there's a lag there. So again, that carbon dioxide remains in the atmosphere for hundreds or thousands of years, and we just have to try and slow the increase. Again, we can't go cold turkey. Our society just we can't do that. We're a carbon-based society, but if we can at least curb some of the emissions and slow the temperature increase, that would make a great deal of help. And then also, again, by the fact that carbon dioxide stays up there for so long, that just kind of locks us into some of the impacts. Things like the rising sea levels, the extreme heat, and things like that. So basically, I think I've answered a lot of the questions that came in on our Facebook page as part of the presentation. Again, I just want to repeat that everything I showed you here is pure science. And in fact, I work with my friends at Climate Central, which is a climate communications organization. They're not an advocacy group. What they do is they take information from the research scientists and turn them into the nice graphics that we see here. I worked on this PowerPoint with them over the summer, and actually, just to give you an idea, even though all the science you saw was already vetted by the scientists who did the research, we took this PowerPoint and I sent it to the executive director of the American Meteorological Society, Keith Sider. He personally vetted this PowerPoint and said it's perfectly fine and it's accurate and he said it was actually very, very good. So what I've tried to do here is simply present the science of climate change, the science of global warming. You'll notice I didn't mention politics in here because there's no room for politics in this discussion. It's simply the science that I presented to you, and I repeat my promise. I will never, ever present you with climate change information that comes from any advocacy groups. You're only going to get it straight from the scientists. So I hope you've gotten a lot out of this. We've been recording this, so we're going to put the link on clickondetroit.com, and once I have that link, I will tweet that link out and put it on Facebook, and we'll let you know so you can share it with your friends and family, or just watch this again if you want, just in case I went too fast through any of the points. So I hope you found this educational. I hope you found it interesting. I just want to wish you, on behalf of all of us here in the Local 4 Weather Office, wish you a very, very happy holidays and a very happy New Year. And with all the snow that we've just gotten, and with more coming this weekend, perhaps we are going to get that white Christmas that we've all wanted this year. Thank you again for watching.